In this video, I want to show you how to determine the pKa or Ka values of a diprotic weak acid using pH titration data, in this case from Logger Pro. The two pKa values of the diprotic acid are the pH values at each half equivalence point. So how does that work? Or how does that make any sense? Here's a little bit of background to rationalize that. So let's just say, for example, we have a monoprotic weak acid. And so if you start with 1 molar acid and you consume half of that, you're at half equivalence point. So if you look at the equilibrium constant expression for a weak acid, and then you substitute in the equal values of the conjugate base in weak acid, you see that those two terms cancel out and you're left with Ka equals H plus. Then if you take the negative log of both sides, you'll end up having pKa equals pH. So to determine the pH values at half equivalence point, the two volumes at the two equivalence points needs to be determined. To do this, we're going to use the second derivative of the pH and volume data. That's one method, and we could do that right in Logger Pro. It's actually quite easy. The other method is using a grand plot, and this is something that's optional for you. You don't need to submit this in your lab spreadsheet or in your lab notes. The grand plot is pretty handy if you don't have the means to generate the second derivative in an efficient manner, or you simply don't want to generate the second derivative of the data. You could add a second derivative plot to the graph. You do so by right-clicking on the graph, Graph Options, and then click on the D2, D1 volume. Then you need to estimate a volume range for the first equivalence point and the second equivalence point. So then you could hone in on the second derivative plot and notice where the second derivative plot line from the max and min cross the volume axis. And so where the second derivative plot crosses the volume axis from the max and the min points, this intersection is the equivalence point volume. Now the second equivalence point is pretty evident. So the first equivalence point seems to be buried somewhere between 12 and 18 milliliters. What I'm going to do is first show you how to determine the equivalence point volume for the second derivative, since it's more evident. To hone in on this part of the second derivative plot, I'm going to change the y-axis max and mins and the x-axis max and mins. One way of determining the equivalence point value is simply putting the cursor over that intersection point and recording 30.50, and I'm getting that value from down here in the bottom left, showing the x and y coordinates. Another way to do this, perhaps more accurately and quantitatively, is to come up here and use this linear fit tool in Logger Pro and click on the latest D2 plot, and you'll see that you'll get a line generated that crosses right through that intersection. We could use this linear equation and set y equal to 0 and solve for x. So off to the side we could set up a little linear equation using this information in this caption and to solve for x when y is equal to 0. So based on this equation, our more exact second equivalence point volume is 30.51 milliliters. So now we could take a look at the first equivalence point, now that we have a means to use the second derivative curve to help us figure out the equivalence point volume. So I'm going to hone in on this area of the titration curve, but I'm going to estimate that the equivalence point is somewhere right here. Simply by a visual, it seems that the equivalence point is right at 15.6. I'm going to add that linear fit. Looks like the first equivalence point volume is 15.71, so a little bit further to the right from where I estimated with that point. So we're going to use these two volumes to help determine what our half equivalence point volumes are. Once we do that, we could determine the corresponding pH at those half equivalence point volumes. So now that we have the volumes at the equivalence points, we could determine the volume at half equivalence point. So for the volume at half equivalence point 1 is simply half of this. And the volume at half equivalence point 2 is the average of these two. And the average is the midpoint between equivalence point 1 and equivalence point 2. With this information, we could go to the logger pro plot and determine the pH at each of these volumes. Now to determine the pH at 7.85, I can move my cursor around the x-axis and get it close with the way the graph is viewed right now, but what I'm going to do is hone in on this volume and pH area. So now I can put the cursor a little bit more accurately right on that volume of 7.85. You can see down in the bottom left corner how many sig figs are displayed. So the pH at that volume is 2.45. So that's our pKa1. So for the pH at half equivalence volume 2, 23.11, see we're right there, and our pH is 4.37, therefore our pKa2 is 4.37. Now I'd like to show you how to use the grand plot method to determine the equivalence point. This is where we don't need the second derivative, and what we're going to do is take volume and pH data in the steepest region of the titration curve. So I'll start with the second equivalence point since it's pretty evident where that is. Now I'm going to intentionally pick some points that are not within the steepest part of the curve. Copy that from the table. The grand plot method requires that you plot the volume on the x-axis, but then something quite unexpected, let's say on the y-axis, which is the volume of the base, and this is specific for a acid-base titration curve, so I'll type VB times 10 raised to the negative pH. 10 to the negative pH looks familiar. You say, well, isn't that the hydrogen ion concentration? It sure is. Where this multiplication comes from is a clever manipulation of the Ka equilibrium constant expression. A video I could refer you to if you're interested in the derivation. But for now, we're just going to follow along with what the y-axis data needs to be for the grand plot. Then what we're going to do is find where the line, because it's supposed to be a linear relationship between the milliliters and this column here, find out where that line intersects the x-axis, which is the volume axis. And where it intersects the x-axis is the equivalence point volume. I'm going to use a scatter plot. As I mentioned before, I intentionally highlighted some of the data that is not part of the most steepest part of the titration curve. You'll end up having data points in your plot that are so close to zero that it deviates from this linear trend that you really want. So I'm going to trim off the volumes above 31. Then I'm going to add a trend line and get the equation. To add more sig figs to the slope and the y-intercept, we'll use the scientific and we'll enter 3. So now what I'm going to do is set y equal to 0 and solve for x, which is the volume at the equivalence point according to the grand plot. Depending on your tolerance for error and your expectations, 30.65 isn't too far from the volume for the equivalence point the second derivative method provided, which is 30.51 mils. To increase the precision between the two methods, smaller increments of sodium hydroxide could be added to the acid solution to increase resolution as the equivalence point is approached. Now I'll collect data around the first equivalence point. According to our grand plot, the volume at equivalence point 1 is 18.16, which is quite different than the equivalence point volume provided by the second derivative plot.